Hello and welcome back to session 4 of chapter Gravitation. Today we're going to solve a few problems based on the chapter Gravitation. So before we begin with the problems, let us first look at the formulas involved in this chapter. So here are some list of formulas which are followed up in the chapter. So firstly, the gravitational force F. The gravitational force F is equals to G m1 m2 upon r square, where G is the gravitational constant, m1 and m2 are the masses of two bodies, and r is the distance between the two bodies. Right? Secondly, from the Cavendish experiment, we are going to give the formula of gravitational constant, and that is G is equals to k theta r square upon m1 m2 into L. So if you remember Cavendish experiment, we have two metal spheres. So the mass of the two metal spheres are m1 and m2. The length of the rod is given by L, and r is the distance between the two metal spheres. Theta is the angle with which the two metal spheres rotate, and K is the restoring couple per unit twist. Okay. Next, the third formula is G is equals to Gm upon r square, where small letter g is acceleration due to gravity, capital G is gravitational constant, capital M is mass of the earth, capital R is radius of the earth. Right? So next, we have Kepler's second law. Kepler's second law says the rate of change of area with respect to time is constant. So we have dA by dt is equals to constant. And the Kepler's third law says the square of the time period is directly proportional to the cube of the semi-major axis. So A is the semi-major axis, T is the time period. So therefore, T square is directly proportional to A cube, right? Next, we have the formula for escape velocity. Escape velocity is square root of 2gm by r. Now we know that gm by r square is equals to g. So if I want to write escape velocity in terms of acceleration due to gravity, I have the formula square root of 2gr. G is acceleration due to gravity, r is radius of the earth. Similarly, orbital velocity is square root of gm upon r, and in terms of acceleration due to gravity, it is square root of r into g. Next, we have the time period of the satellite. So we have 2 pi root r upon g. Okay, and height of the satellite, we're going to give it by t square r square g upon 4 pi square to the power 1 by 3 minus r. So these are some of the formulas which are listed in this chapter. Now let's solve one by one some problems to know more about how we are going to apply whatever we have learned in the theory part in the problem part. So the first question says, calculate the gravitational force between two metal spheres weighing 4 kg each and 0.2 meter apart. Given G is equals to 6.67 into 10 raised to minus 11 Newton meter square per kg square. So firstly, what we have to do here is we have to write down what are the given quantities and what is asked. So what are the given quantities? So given quantities here, the first one is G is equals to 6.67 into 10 raised to minus 11 Newton meter square per kg square. So this is given to us. Now next, what is given to us? Two metal spheres weighing 4 kg each. So that means M1 is equals to M2 is equals to 4 kg. Right? And they are kept 0.2 meter apart. So therefore, the distance between them is 0.2 meter. So what is asked? Calculate the gravitational force. So F is asked. So what is the formula for this? F is equals to G m1 m2 upon r square. So now we have the values of G, M1, M2, R. Substitute, what we get? 6.67 into 10 raised to minus 11 into 4 into 4 divided by 0.2 square. Right? So if you simplify this, this is nothing but 2 into 10 raised to minus 1. If I write this, I will get it as 4 into 10 raised to minus 2. And 1 4 and 1 4 gets cancelled. So I can write this as 6.67 into 10 raised to minus 11 into 4 divided by 2 into 10 raised to minus 1 the whole square. So 0.2 I can write it like this. If you have a calculator, you can directly put the values and you can simplify it. In case you don't have a calculator, you can follow this method. So we have this to be 6.67 into 10 raised to minus 11 into 4 divided by 4 into 10 raised to minus 2. 2 square is 4. 10 raised to minus 1 square is 10 raised to minus 2. So 1 4 gets cancelled. So what is 4 into 6.67? 4 7s are 28. 4 6 are 24, 26. 4 6 are 24, 26. 26.68. This minus 2 goes up. So I have 10 raised to minus 11 plus 2. So it is going to be 26.68 into 10 raised to minus 9 Newton. And this is the gravitational force which we had to calculate. Right? So the second problem says calculate the value of G on the surface of the earth from the following data. So this is the data given to us. So what is given to us? So our first step is we are writing what is given to us. First, what is given to us? Mass of the earth. I will write it as ME. So this is equal to 6 into 10 to the power 24 kg. Radius of the earth RE is equal to 6.4 into 10 raised to 6 meters, and gravitational constant G is given as 6.67 into 10 raised to minus 11 Newton meter square per kg square. And what is asked? Calculate the value of G. So G is asked. So what is the formula? G is equals to Gm upon R square. So we'll put that here. It is Gm upon R. So G is given, M is given, R is given. Substitute. So we have 6.67 into 10 raised to minus 11 into 6 into 10 raised to 24 divided by 6.4 into 10 raised to 6 the whole square. So using the calculator, if we try to find the value, we get the answer as 9.77 meter per second square. So this is acceleration due to gravity. So approximately we know that G is equals to 9.8 meter per second square. So whatever answer we've got is approximately equal to 9.8. So we can say that our answer is correct. Right? So this is our second problem. Moving on to the third one. The third problem says calculate the mass and density of the earth from the given following data. So data is given to us and we have to calculate the mass and density of the earth. So what is given to us? Given, again we'll write it, G is equals to 6.67 into 10 raised to minus 11 Newton meter square per kg square. Radius of earth is given 6.4 into 10 raised to 6 meter. G is given 9.8 meter per second square. And we are asked to calculate the mass of the earth and the density of the earth. So how do we calculate the mass of the earth? Now, since we know small g, this is equal to gm upon r square. So from this I can calculate what is the value of m. So here we have g is equals to gm upon r square. So this implies m is equals to what? This r square comes on the other side. So we have g into r square, and this capital G comes below. So we have divided by g, right? So if we substitute the values, we get 9.8 into r is 6.4 into 10 raised to 6 the whole square, divided by g is 6.67 into 10 raised to minus 11. So if we simplify this, we get the value to be 6 into 10 raised to 24 kg. So this is the mass of the earth. And secondly, we have to calculate the density of the earth. So to calculate density of the earth, we have to use the formula density is equals to mass upon volume. Now mass value we have found out. What is volume of the earth? Since the earth is spherical in shape, we write volume of the earth to be equal to 4 by 3 pi r cube, volume of the sphere. So we write it here as m divided by 4 by 3 pi r cube. So this 3 goes on top since it's in the denominator. So we have 3m by 4 pi r cube. So m value we know, r value we know, substitute. So we have 3 into 6 into 10 raised to 24 divided by 4 into 3.14 into r is 6.4 into 10 raised to 6 the whole cube. So this sums up to 5.6 into 10 raised to 3 kg per cubic meter approximately. So this is the value of density of the earth, right? The fourth problem says a body weighs 60 kg on the surface of the earth. How much will it weigh on the surface of Mars, whose mass is 1/9 and radius half that of the earth? So here what is given to us? Mass of Mars, mass of the body on Mars, this is equal to 1/9 time mass of the earth, okay? And radius of Mars is equal to half that of radius of earth, right? And they have given that a body is weighing 60 kg on the surface of the earth. So that means this F on earth, force, gravitation force on earth, this is equal to the weight on the earth, and the force on the Mars is equal to weight on the Mars. So that means G mass of earth, okay, into mass of the body divided by RE square, this is equal to FE, and FM, or I can say WE, weight on earth, and this is weight on Mars. This is equal to GMM into M upon RM the whole square. The mass of the body is not going to change whether it is on the earth or on the Mars. So it is going to remain the same. Now if I divide this by this, that is if I divide Wm by We, that is weight on Mars divided by weight on earth. So I will get GMM into M upon RM the whole square divided by GME M upon RE the whole square. So this M is cancelled. G and G will get cancelled. Okay. So MM by RM the whole square divided by ME by RE the whole square. This I can write it as MM by RM the whole square into RE the whole square upon ME. But what is MM? MM is 1/9 of ME and RM is half of RE. So this is going to be 1/9 of mass of Earth divided by half of radius of Earth into whole square into RE the whole square divided by ME. So this ME and ME gets cancelled, RE square gets cancelled, but this half is also squared. So I get this to be 1/9 divided by 1/4, that is equal to 4/9. But what is this? This is the ratio of weight on Mars, divided by weight on Earth. So this is equal to 4/9. But what is the weight on Earth? This is 60. So I can say weight on Mars is equals to 4/9 into weight on Earth. So if I calculate that, I will get 4/9 into 60. This is weight on Mars. So if I calculate this, this comes around 26.67 kg. So this is the weight on Mars of the body whose weight was 60 kg on the surface of the Earth. So this is our fourth problem. Let's move on to the fifth one. The fifth problem: calculate escape velocity of body of Earth from the following data. Body on Earth from the following data. So this is given to us and we have to use the value of escape velocity, what we have calculated here, to find the escape velocity of the body on the surface of the Mars, where mass of Mars is 1/9 mass of Earth and radius of Mars is half radius of Earth. So firstly, let's calculate the escape velocity on the Earth. Okay, so what is the formula? It is square root of 2 gm by r. So mass of Earth, radius of Earth, right? So this is escape velocity on the surface of Earth. So I'll denote it as VEE, and mass of Earth is ME, radius of Earth is RE. So substitute the values. So we have square root of 2 into 6.67 into 10 raised to minus 11, 6 into 10 raised to 24 divided by 6.4 into 10 raised to 6. So when we simplify, we get the answer to be 11.2 kilometer per second. So this is the answer we are going to get, right? Now we have to use this escape velocity to calculate the escape velocity of the body on the Mars. So escape velocity on the surface of Mars. So this is going to be square root of 2g mm upon rm. So that is mass of the Mars and radius of Mars. So this I can write it as 2g. What is mm equal to? 1/9 of me divided by rm is half of re. So now I'll just remove this 2gme upon re separately. So I get that as square root of 2gme by re into, what is left? 1/9 is left on top and half is left below. Square root. So what is this? Square root of 2 GME by RE is nothing but VEE. So I get square root of this 2 goes on top, 2/9 into VEE. And what is the value of VEE? It is 11.2. So square root of 2/9 into 11.2, I get approximately 5.28 kilometer per second. Approximately 5 kilometer per second. So this is the velocity or escape velocity of the body on the surface of Mars. Right? So let's move on to the last problem of this chapter, that is the sixth problem. The sixth problem. A satellite revolves in a circular orbit at a distance of 1620 km from the surface of the Earth. Calculate the orbital velocity and time period of revolution of satellite given radius of Earth is 6380 km, mass of Earth is 6 into 10 raised to 24 kg and gravitational constant G is 6.67 into 10 raised to minus 11 Newton meter square per kg square. Now we know that orbital velocity formula root gm upon r. So here, since the satellite is revolving around the Earth and it is at a distance of 1620 km, so if I consider this as h, right? So I will have the orbital velocity to be square root of g m e upon r e plus h, because the total distance is re plus h. So this I'm going to substitute it like this. So we have square root of 6.67 into 10 raised to minus 11 into 6 into 10 raised to 24 divided by, what is RE? 6380 plus 1620. I'll keep it like that only because both are in kilometer, right? So if I simplify this, I get it around 7.07 kilometer per second. So this is what I'm going to get when I simplify this, right? So this is addition. You have to add these two and then multiply this, divide by this. It's a simple mathematical calculation. So you can do it in your calculators. The next, what we have to find out is the time period of the revolution of the satellite. Time period, it is given by t is equals to. Now, what is the time period? Right? So velocity is distance by time. So distance here is going to be the circumference of the circle, that is 2 pi r and t. So this is going to be our orbital velocity. Now since we are calculating the time period of revolution of the satellite, this will become 2 pi into r plus h, and this v0 comes down when t comes here. So divided by v0. So substitute, we get 2 into 3.142. Again, we'll substitute 6380 plus 1620 divided by orbital velocity is 7.07. This is also in kilometer, this is also in kilometer. So if I calculate this, I will get this as 1.97 hours. So this is the time period of revolution of the satellite around the Earth. So this is how we are going to solve all the problems. So using the formulas, you can simplify or you can analyze what is given to you. You can analyze what is asked, put up in the formulas and you can simplify and solve the problems. So this ends the chapter Gravitation. I hope you've all understood each and every point in this chapter. Thank you.